The Symmetries of Spacetime by Kate, Matthew, Nat, and Noah. Are you an agent in 4D Minkowski spacetime? Well, we're going to study Einstein's theory of special relativity using group theory. Keep listening to find out why Lie groups and the Lorentz group, aka space and time itself, do not allow you to change something that's happened when changing between reference frames. Part 1, Lie groups and the Lie algebra.
Okay, so the definition of a Lie group is a group that is also a differentiable manifold. And that's kind of a mouthful, but basically we can imagine our Lie group as a bunch of smoothly connected points on some blob in space, where the blob is the manifold. And also the group operation must be smooth. So this means that small changes to the inputs result in small changes to the outputs. And that's what differentiable means, as we all know from calculus. Because they're all smooth, Lie groups are infinite continuous groups. And a big advantage of Lie groups is that we can apply calculus in addition to our other group theory tools. And also, since they can be represented as points on a manifold, we can also study them with topology. So to see an example of a Lie group, we can look at the circle group, which can be represented by the set of complex numbers of magnitude 1 under the operation of multiplication. And we can just write this as e to the I phi. And this is a group because it's closed under multiplication and inverses. So if you multiply e to the I phi 1 times e to the I phi 2, you just get e to the I phi 1 plus phi 2, which is just another point on the circle with a different angle. And similarly, the inverses are the negative of the angle, because that takes you back to 1 on the real axis. And this is also a differentiable manifold because it's a smooth collection of points in two-dimensional space. So therefore, the circle group is a Lie group. Some other examples of Lie groups are R, R2, and R3, just the whole spaces. SO3, which is the rotations in 3D space. And then S3, which is the 3-sphere in 4D space, and the rotations of that sphere. And then we also have higher dimensional Lie groups, like GL of N and R, where GL is just the general linear matrices in n dimensions that are real valued. Some important ideas about Lie groups. First one is the dimension of a Lie group, which is just the dimension of its manifold. Or we can also see the dimension of a Lie group as corresponding to the minimum number of parameters needed to uniquely specify an element of the group. So for example, the circle group has dimension 1 because we can specify any point on the circle by an angle, whereas R3 has dimension 3, as we all know. And then a Lie group is connected if there's a continuous path between any two group elements, and it is simply connected if it has no holes in its structure. So this photo shows that the first two are both simply connected. The third picture is not connected at all. And then the fourth one is connected, but not simply connected. So this is just a fun example of a manifold called a Klein bottle. And it's a non-orientable shape because if you try to draw an arrow going outwards, you'll see that it will be on the opposite side of the surface. And does not form a Lie group, but it just is a fun manifold. So Lie groups have very important relations to symmetries because symmetries are changes that don't change a specific property of an object, such as the rotations of a circle, which as we saw, form a Lie group. And in general, every symmetry of a space corresponds to a unique group operation on the points in that space because symmetries, by their nature, don't change a certain aspect of a group and therefore keep the group closed. And they are also reversible. And Lie groups are often applicable in physical situations exactly because they deal with continuous symmetries. So just taking a quick break from all the math, we just have a slide with an asymmetrical beaver here. Yeah, it does not form a Lie group.
A really important area in the study of Lie groups is the theory of a structure called the Lie algebra, which we can associate with the Lie group. I guess the motivation for introducing this structure called the Lie algebra is that Lie groups can be highly nonlinear. So if you think of a parameter that describes a rotation group, for example, the group operations will be very nonlinear in that parameter because it'll involve sines and cosines. And in general, higher order groups of rotation and other operations involve nonlinear terms, which make these groups hard to study. So what's the solution to the difficulties presented by this nonlinearity is to simply linearize your group, and that's where the Lie algebra comes in. So the elements that we define this Lie algebra on are the tangent space at the identity of our Lie group. So for a more concrete example of what that means, we can look at the circle group on the left here. Our identity is the element at 1 on the real number line, and then the tangent space is that line passing through the identity, and we can describe that by this line I theta. And so the exponential map maps this tangent space onto that group structure. And in higher dimensions, we can think of the same thing. So in the sphere on the right, our tangent space is this plane, which is tangent to that point on the sphere. So these elements constitute these elements of the tangent space make up the element of our Lie algebra. And on these elements, we define an operation called the Lie bracket, which I'll talk about more later, but essentially is a commutator. So it tells you to what extent that group is non-abelian. And so we devise this vector space consisting of elements in the tangent space at the identity of the Lie group, along with like addition and this operation called the Lie bracket. Now, what are some really important properties of the Lie algebra? So first of all, the dimension of the Lie algebra is equal to the dimension of its corresponding Lie group, which, as we mentioned before, is a number of free parameters as we move through that manifold. And so every element can be represented as the sum of basis elements called the generators. And you'll have the same number of generators in your Lie algebra as the dimension of your Lie algebra. This is the exact same concept as the generators that you would have learned about in linear algebra. And so the generators are important because they allow you to understand infinitesimal changes along the different directions in your Lie group. If you imagine multiplying your Lie group element or your Lie algebra element by an infinitesimal amount and then exponentiating that, you'll get a very small rotation in your group. And so in that sense, we can think of these elements of the Lie algebra as generators of infinitesimal movements of our Lie group. And so this gives us a really useful vocabulary to talk about generators of the Lie group, which are more difficult to talk about than generators of finite groups. And so now more on this operation on the Lie algebra called the Lie bracket. As I mentioned before, it quantifies how elements commute. In other words, to what extent the Lie algebra and thus the Lie group are non-abelian. And so one example of what a Lie bracket could be defined as is the cross product, which is what you would use if your Lie group is in R3, or the matrix commutator. So it's just AB minus BA, and you would use that for like your matrix Lie groups. Now, why is this useful? So in general, linear properties are way easier to deal with. We can derive interesting things about linear algebras much more easily than we can non-linear algebras. And so in physics, for example, fundamental forces are described by operations of Lie groups. And so we can look at the Lie algebra, essentially the linearization of this Lie group, and much more easily calculate properties of these fundamental forces. Now, let's dig in a little deeper onto what exactly this exponential map is and where it comes from. So we see in this first image at the top that you can write an infinitesimal rotation in 2D space by this matrix, and we can split it up into the identity plus this differential rotation around LZ, which is that matrix on the right over there. Now, if we want to take this tiny rotation and make it into a finite rotation, we can simply take a limit as that differential goes to 0 and applying that a number of times around this angle theta, and it turns out that when we write this equation out, we get the limit that we're all familiar with that gives you the exponential mapping, e to whatever element you have there. And so this is how we see that the exponential map takes these small elements in our Lie algebra and rotates them into elements of our group. And in this case, this matrix LZ would correspond to the rotation around the z-axis, and it would be the generator of our Lie algebra. But this analysis only extends to one dimension in our Lie group. So what if we have higher dimensions? So if A and B are elements of our Lie algebra, it's not generally true that e to the A times e to the B equals e to the A plus B. We could see that that's true in our circle group, for example, where we're just working with real numbers. And in this case, the property that makes that work is that the group is abelian, so this is fine. But if we have a non-abelian group, then we need a higher order formula in order to understand this mapping between our Lie algebra and our Lie group. This is where we see this new formula where we have e to the A, e to the B equals e to A plus B plus some higher order terms that are made from the commutator, the Lie bracket of those elements in the Lie algebra. This is called the CBH theorem, and it leads to a lot of really important results in the analysis of Lie algebras and Lie groups, because it gives you this really important way of how to connect the algebraic structure of your Lie algebra in terms of addition and the Lie bracket into the algebraic structure of your Lie group, which is ultimately the thing that you're really fundamentally interested in understanding. And so if we just take a look at this picture of this sphere, we see we have different generators in the different directions of that tangent space, and the exponential map wraps those different directions around the sphere. And because this is non-abelian, we would need to use that CBH theorem to get the group structure in terms of the commutators as well.
Part 2, Lie groups and the structure of spacetime.
So to understand this next section, it's really important to understand the idea of reference frames and coordinate transformations. So in physics, a really important idea is the idea of perspective, which physicists call the idea of a reference frame. And so examples of reference frames might be an Earth-based reference frame, where an observer is standing on the ground. But it could also be a plane-based reference frame, where an observer is sitting in a plane. And when we change reference frames, our perception of space-time changes. We no longer agree where and when events will happen. So for example, an observer on the ground will think that the wing of the plane is moving, but the observer in the plane thinks that the wing seems stationary. So a big question now is, what are the ways that space-time is allowed to transform when we move between reference frames? Now, something all observers must agree on, regardless of reference frame, is causality. Can two events influence one another? So, for example, we can kind of have the intuitive idea that what we do right here and now can't influence what's happening in another galaxy, because that galaxy is just too far away for us to be influencing right now. So we have this idea that events can be causally disconnected if the spatial distance is greater than the time distance. On the other hand, they can be causally connected if the time distance is greater than the spatial distance. Given enough time, whatever we do right now will influence what happens in another galaxy. So to quantify this idea, we can introduce the space-time interval. And roughly the space-time interval is distance in space minus distance in time. And so the distance in space is delta x squared plus delta y squared plus delta z squared. And then the distance in time is delta t squared. And this quantity is called the space-time interval. And so in order that all our reference frames preserve causality, we require that all our coordinate transformations preserve this space-time interval. So to find the allowed space-time transformations, we want to consider the set of all linear coordinate transformations that leave the origin unchanged. So therefore we can represent each transformation as a matrix A, where the transformed coordinate is equal to A times the original coordinate. So the distance between any two events can now be written as a vector, dx, which is equal to delta t, comma, delta x, comma, delta y, comma, delta z. And we see that this distance between events transforms using the same matrix. So now we also notice that the space-time interval can be written as a matrix equation. ds squared equals x transpose gx, where g is this special diagonalized matrix called the metric. So now using linear algebra, we want to require that the space-time interval is preserved whenever transforming coordinates. So we enforce that x transpose gx is equal to the transformed coordinate times g times the transformed coordinate. And this results in the equation g equals a transpose ga, where so any coordinate transformation must obey this equation.
So now we're going to dive into the Lorentz group. The Lorentz group describes, or it is the group of space-time transformations that correspond to observing an event from different reference frames. And again, this is preserving our space-time interval, which we see here. The elements of this group are 4x4 matrices that are acting on our event, which is a 4-vector, because in our reality we have 3 dimensions of space and 1 of time. There are 6 generators of the Lorentz group, and they correspond to 3 rotational generators. In our 3 spaces, we can think of that as rotations around the x, y, and z axis. So when combined, those can describe all rotations in our 3 spatial dimensions. And then also 3 generators that are called boosts, which go into different moving reference frames. And in that case, we can think of it kind of as the movement around x, y, and z axes, but also it's a little bit different than that because it has to account for this preservation of our space-time interval. So it includes things like the Lorentz transformation, which is how you move between different reference frames.
So as Kate had talked about, the Lorentz group is the set of 4x4 matrices that satisfy this condition, G equals A transpose GA, where G is the special diagonal matrix. So this equation allows for 6 degrees of freedom, and therefore our group lives in 6-dimensional space. So the Lorentz group is a continuous subgroup of a matrix group, so it's a Lie group, but unfortunately it doesn't have a simple structure like the Lie groups we had already looked at, such as the circle group. So for example, the Lorentz group is not actually connected, so it's not one blob in 6-dimensional space, but it's actually 4 disconnected blobs in 6-dimensional space. These blobs each have an interesting physical interpretation.
So our Lorentz group is a Lie group, and as we talked about before, a Lie group is also a differentiable manifold. And as Noah was saying, the Lorentz group has 4 components, which are each in themselves connected. They can be characterized in terms of 2 of the following properties, and that's the preservation of the direction of time and the preservation of the parity of space. You can think of this as, since they're just conserving the space-time interval, which has the squares in them, as being, these transformations can also be ones where, time or space, their parity or their sign are flipped. So the manifold components, each of them is a different combination of these properties. One thing I wanted to briefly mention about the disjoint components of the Lorentz group is that we can use the determinant to determine whether a specific generator or a specific transformation that's an element of our Lorentz group flips the parity of space. If the determinant of the matrix is equal to +1, then the parity of space remains the same. If it's -1, then the parity of space is flipped. And we can see that how that is related to putting in real or complex values into our generators and getting out different values, either plus or -1 for the determinants. All right, so actually only one of these components or these manifolds within our larger manifold contains the identity element, and that is called the identity component. And because a Lie group is a topological group, there's actually a theorem that says the identity component of a topological group is a normal subgroup. So that means that our group that we call our subgroup of the Lorentz group, that's called the proper orthochronous Lorentz group, which just means that it preserves the parity of space and it preserves the direction of time. That means that that is a normal subgroup of the Lorentz group. So then that means we can find cosets of H and then use our quotient, form a quotient group. So I have listed the 4 cosets of H, and they actually correspond to our 4 components of our manifold. So that is when the component where just time is reversed, where just the parity of space is reversed, and where both are reversed. And then of course our proper orthochronous Lorentz group has the parity of space and the direction of time preserved. So something interesting is that we can use Theorem 5 in Chapter 15 to confirm that these are the cosets of H, and actually I'm going to go through a brief outline of the proof to show that for 2 elements in one of these components, that they are in the same coset. Okay, so a brief outline of the proof involved. Every element in the Lorentz group can be described as an element in the proper orthochronous group, up to a parity of space and direction of time. So we have these kind of elements in our components that we can use as almost identities of their specific reversal. So the matrix I defined as IT, for example, I define it as like the time reversal operator. So it's something that only changes the time direction when applied to the matrix. So note that if any element, say T in the component, we're going to go with capital T, which is going to be the time reversing component, we can write that as either a right or left-handed product of an element in the proper orthochronous group with a time reversal operator. And we notice that in the representations of our time reversal operator or time reversal element, that's our identity in a sense, that it's its own inverse. So if you flip time once and then you flip it again, it goes back to what it was originally. So it follows that if we use our Chapter 15 Theorem 5, we can show that that HA equals HB if A times B inverse is in H. So then we have that A times this time reversal identity times, again, the time reversal identity times B, where A and B are the components of the proper orthochronous group that when multiplied with this time reversal identity are our original A and B inverse. Then we notice that we can use associativity and show that that is equal to AB, which is then again an element of the proper orthochronous group because they're both elements of the group and the subgroup is closed under the group operation. And this logic also works for the components PT, which is the reversal of both time and the parity of space, and also P, which is just parity reversal. So then we have now a group of cosets because the quotient group, we can form the quotient group because H is a normal subgroup of the Lorentz group. And because it is has order 4, then we know that it's also abelian. So that's just a fun little connection to our class. Part 3, Lie algebra of the Lorentz group.
So now let's take a quick look at the Lie algebra of the Lorentz group. So even the proper orthochronous Lorentz group has a pretty complicated structure, so it's helped us study its Lie algebra instead. The proper orthochronous Lorentz group, it's not abelian, it's not simply connected. So studying the vector space, the linear Lie algebra is a lot easier. So remember that the exponential map takes elements of the Lie algebra and maps them into the Lorentz group. So therefore we can define the elements of the Lie algebra as follows. It's the set of all 4x4 matrices such that e to the a maps into the Lorentz group. So working through this algebra, it turns out that the only matrices that satisfy this condition take on the following form. And there's zeros along the diagonal, and then you have some combinations of A, B, C, D, E, and F in various locations where A through F are real numbers. So notice that this has 6 degrees of freedom, meaning that the dimension of the Lie algebra is the same as the dimension of the Lorentz group, which is what we wanted. Also notice that in this form, it's pretty easy to see what the generators of the Lie algebra are. Just let A equals 1 and have B through F be 0, or let B equals 1 or C equals 1, etc. So now we want to find out what these generators what the generators in the Lie algebra map to in the Lorentz group. As Matt had talked about, the Lie algebra structure completely determines the Lie group structure. So if we study what the generators of the Lie algebra map to in the Lorentz group, we can kind of have a better understanding of the Lorentz group. So to go from the algebra to the Lorentz group, we just apply e to the a, and this is what we get. So on the right here are the generators that we found by looking at the possible matrices that belong in the Lie algebra. And then on the left, we see what these generators map to under the exponential map. So we notice that this tells us that looking at those generators, we see that there are kind of 2 types of space-time transformations. So this first one, it looks like you have a combination of cosines and sines and then ones and zeros. And so this is the rotation matrix corresponding to a spatial rotation about the x-axis, leaving time unchanged. So that means that rotations in space preserve the space-time interval, so they are a valid space-time transformation. On the other hand, we have these other types of space-time transformations. They seem to have hyperbolic cosines and hyperbolic sines, and they mess with the first row and column of the Lorentz group, meaning that time is affected. So these correspond to boosts. This, in particular, this is a boost along the x-axis. So this type of transformation actually mixes space and time coordinates, which has the interesting implication that time is not actually universal for all observers. So if we study this hyperbolic type of space-time transformation, it turns out that this exactly maps to the Lorentz transformation, which is really one of the pillars of Einstein's special theory of relativity. So that means we could have arrived at this Lorentz transformation just through group theory and requiring that the space-time interval be preserved, which I think is a really cool application of group theory.
And finally, here are the links to the resources we used. Thanks for listening.